Well, thank you so much. Yeah, as Shauji said, I'm Kashif from Morgan Stanley, and I'm really honored to be talking here at this seminar. And I also want to thank you, the organizer, for organizing it. As you know, Morgan Stanley is also sponsoring this seminar, and so I just wanted to quickly highlight that at Morgan Stanley, we have a research team that is also working in many areas of machine learning, like deep learning, and in particular looking at problems of recommender systems, graph neural networks, and also NLP as well. And believe it or not, we also have use a lot of the open source frameworks and tooling, as well as cloud infrastructure that people are kind of familiar with from academia or kind of tech companies. And so the transition here, for me at least, has been somewhat familiar as well. And finally, what I wanted to say is that Morgan Stanley, and especially the AI Research Lab, has been actively kind of partnering up with academics as a part of the, and also external research community by sponsoring conferences and seminars like this, as well as inviting external speakers. And so this week, for example, we're at our booth at ICCV, and we will be sponsoring iClear, UAI, and also EM NLP. So I hope many of you will drop by our booth at these conferences as well. So, and finally, you can always contact us for more information, or if you would like to share your research work, as we have also a research talk series that you can sign up from the AI seminar homepage as well. Cool. So I thought for today, I wanted to introduce you to some aspects of neural forecasting, in particular, probabilistic neural forecasting, and then build up to then introduce you to some of the recent works that I have done in this area of multivariate time series, probabilistic time series forecasting. So yeah. So let's jump right into it. As you can imagine, time series forecasting has important scientific and industrial applications. But these classical methods, which typically need to be trained individually for each time series in a data set, don't scale when we have to deal with, say, millions of time series in industry. Right, so deep learning methods are well suited for such situations where we typically have a single shared or global model trained end-to-end over all the time series in the data. And these models allow us to incorporate exogenous covariates as well as other deep learning architectures quite easily. And so they're becoming super popular. And modern point forecasting methods can be constructed by taking inspiration from NLP, say via sequence-to-sequence methods, or taking inspiration from convolutional architectures by using, say, temporal convolutions, which the organizer, Xiaoji, has worked on. And more recently, even using attention-based architectures as well. And these models can be constructed to output some a prior fixed size prediction window, or in the case of RNN, we can also construct autoregressive forecasts for arbitrary prediction horizons as well. And typically, point forecasting methods are trained by minimizing, say, the mean squared error of the final output with respect to the ground truth training data. And modern takes of this approaches are architectures like temporal convolutions, or things like NBeats, where, for example, you where you use forecast not just the future, but also try to reconstruct, in some sense, the backcast as well, and learn representations that way. Nevertheless, you can make all these architectures arbitrarily complex and deep. And so typically these modern methods perform quite well empirically. The problem of modeling uncertainty is also of vital importance, especially for assessing how much you trust the predictions for the downstream tasks that typically use these forecasts in some business context. Right? With just point forecast, the importance of the prediction in regions of low versus high noise cannot be distinguished. Thus, the idea here is to learn the data distribution for the time steps into the future via what we call univariate probabilistic forecasting methods, which I will describe next. Also, individual time series in a data set in many cases are statistically dependent on each other, and models might need to account for this inductive bias via what we call multivariate forecasting. For example, you can imagine in a traffic flow network, a disruption in one street can have a ripple down effect on nearby streets, and univariate methods that assume independence between all the time series would not be able to account for such effects. So let me first describe the univariate probabilistic forecasting problem. Right? More formally, we will denote the individual time series from our data set of, say, capital D time series by xi. Right? So that's one of the time series in our data set, and index this time series by the time index t. Right? So, and then our data set is composed of these capital D time series, where we split the data set into a training window, right? A training window and a held out validation window, which you can see on the picture here, right? And essentially it consists of the same time series, but with longer histories, right? Longer histories. For training, we typically use a sequence to sequence approach where we construct batches by randomly sampling a context window and an adjoining prediction window to construct these batches for training our models. Right? And more importantly, and unlike say in NLP, which also has sequence of tokens, here in the time series setting, you have a sequence, you have this extra time variable t, which embeds in some sense the time series into the real world. And in the real world, for example, there are seasonal effects that can be incorporated as well into our model. And therefore, one can use the time index here to construct what we call covariates. For example, say if the hour of the day of the week of the month, and depending on the frequency of the data set. And then these features can also be concatenated to the actual values of the time series and then the model, we can define our probabilistic time series model as a model that learns the distribution, the probability distribution of the future, given the past, as well as all the covariates in the future as well. And typically, if you model this distribution via some autoregressive model, then you want parameterized by theta, then this probability kind of factorizes out like that. So you want to learn the probability of the next time step given the past together with the covariates associated with that time series. Okay, we have a question. These seems to use, right. So that's one correct. But remember, these covariates are time covariates. So the question was, there seems to be covariates. We need to know the covariates in the future where we are in some sense forecasting, and that is true. But these are time covariates, meaning I know in the future what day of week it is, what week of month it is, and so forth. In fact, maybe the next slide is about covariates, right? And then there, those would be those are the time features which we know about, but each time series I can also embed, give it a kind of an associated embedding vector, which also doesn't change in time, so also know that in the future. Also, the age of a time series, depending on kind of the frequency, is something that I also know in the future because it's just increasing incrementally. So that again, I know in the future. Finally, holidays as well are somehow repetitive events, which are known when they will happen in the future as well. And so the holidays, you can encode them as a bed of nails in the time, on the time axis. And then you can also smooth them out via a kernel so that the network in some sense knows when a particular holiday is approaching or has gone by, right? And so a lot of the work in with these covariates involves kind of figuring out these kind of features that can potentially help the forecast, which is in some sense different to say NLP or just pure sequence modeling, where you don't have kind of this aspect. I hope that answers your question. So I said we want to learn the distribution of the next time point. And in fact, that's what the DeepAR model is essentially doing. What we do is we encode the history of a time series up to some point t-1 in by a hidden state of an RNN. Right? So this hidden state then takes in the actual value at t-1 as well as the covariates together with the previous hidden state to output the next hidden state. And then what we want to do is model the distribution of the next time point given this hidden state, right? Where the parameters are living in the RNN. And then at each time point, we want to output parameters of some chosen data distribution. So for example, we can say our distribution is normal. Then we want to output, see your application. Okay. Then if we say our distributions is a normal distribution, then we can output the mean and the variance parameter. And we can also model other parametric distributions that way as well. In pictures, it kind of looks like that. You have your RNN. You have your concatenation of the time point t-1 together with the covariate. And you output from the hidden state, you output and then a neural network that outputs two numbers, mu and sigma, with the caveat that the sigma has to be positive. So you can add a nonlinearity here that makes the sigma positive. And once you have these two numbers, you can instantiate, say, the normal distribution and maximize the log probability with respect to the ground truth next data point, next time point, right? And you train your model this way within your training window, your full training window. At inference time, then what you can do is you can run your RNN over some context length window and obtain some hidden state, and then from this hidden state output the mu and sigma, and again instantiate the normal distribution, and now you can sample from this normal distribution. Right, so it would be something like that if you had a purely linear activation. Yeah. And then, but here, because of the RNN and kind of the covariates here, we're learning kind of a nonlinear model here, nonlinear autoregressive model. for the distribution of the next time point into the future. And then at inference time, you can sample and then pass this sample back into the RNN and continue to forecast as much as you want into the future that way. Not only that, but you can do this process of sampling many times, and then you end up with many samples of the future, and then from that you can calculate statistics that you're interested in of the future. So here's an example of that. At this point, I start forecasting, and I not only forecast once, but forecast say 200 times, and then from those 200 samples, I'm able to calculate quantiles that I'm interested in particular the mean, the medians, as well as the standard deviations and so forth. Any questions till now? No. Okay. So what about multivariate forecasting? Well, a simple model for multivariate value data could use the same architecture as DeepAR, where we now encode the history of the multivariate vector and its associated covariates, and then share parameters in the temporal encoding layer in the RNN can learn patterns across all the entities. But to output the dependencies in the emission, we need a full joint distribution head for each time point, right? For example, via multivariate Gaussian. So the issue then is that the full covariance matrix we would need to output would increase the number of parameters by say d squared, where d are the total number of my multivariate vector. And more importantly, to calculate then the log probability, we would need to do a order d cube operation, making this kind of impractical for very large multivariate problems. Right? That's not to say people have tried. People can use a diagonal independent distribution or a low rank approximation to the covariance matrix, which does alleviate some of these issues and gives very strong baseline models as well. But what we wanted to do was to kind of try to learn a general distribution of the data where this D dimension is very large. So we can take inspiration in some sense from generative models in the image coming from the generative image community. So what we do in the first work is we propose to use normalizing flows to model the distribution of the multivariate time series so that we're able to train and sample from it at inference time in a kind of computationally tractable and general manner without specifying, for example, that the distribution has to be a low rank Gaussian or some cupula or something easy for us to kind of evaluate with. So what are normalizing flows? I assume people, well, you might know what they are, but maybe it's a good refresher as well. So let me just quickly talk about those, and then I'll show you how that works in the time series setting as well. So normalizing flows are essentially defined as a sequence of invertible mappings from some vector space to itself. And these mappings need to be differentiable and invertible. So invertible means that they the dimension of the input and output has to match. And the idea is relatively simple. What we do is we want to approximate. Well, what we want to do is we want to learn a sequence of these invertible mappings from some vector space to itself, given by neural networks, with intuition that we transform our complicated data distribution into some simpler one, like an isotropic Gaussian. Then, if we have such a mapping, we can maximize the log probability of the data with respect to the simpler distribution. And sampling from this, from the complicated distribution also becomes easy, because what we need to do is we sample from the simple distribution, like the Gaussian, and then run the transformation backwards, right? Essentially, that's what you see here are samples from the complicated distribution, where you're kind of moving smoothly in the simple distribution. So in order to be useful, normalizing flows need these two properties: that the inverse operation is easy to evaluate, right? So you can easily go backwards from the simple to the complex, and the determinant of the Jacobian of the transformation coming from the change of variable formula, I'll show you that in a second, is somehow tractable as well. Right, so if you have these two properties of a sequence of bijections, then that's what a normalizing flow is in some sense. And as you can see here, it's been used quite successfully to learn from very high dimensional probability distribution like natural images, as in the GLOW paper by from the OpenAI researchers. Okay, so yeah, let me give you some intuition about what's going on here. So suppose we have samples from some complicated distribution P of X, right? So this constitutes our data set. And what we want is a differentiable and invertible function F, where F of X will be a sample Z here, right? Such that this mapping such that this is a mapping to a simple distribution. So P of Z is some simple distribution like a Gaussian. However, because this mapping needs to be a distribution, we need to take into account the volume here, and so that everything has the same volume. So we want to preserve the volume so that the output here continues to be a distribution as well. And so this volume preserving term then introduces a determinant of the Jacobian of this function here. And so that's where this determinant comes from. And you can imagine the determinant of the Jacobian then is a D by D matrix. Yeah. Capital D by capital D matrix. All right, so then training is relatively simple. You just maximize. So if our F, we had is relative simple, you just maximize the log probability of your data, of this data. But because of this this transformation, it's maximizing the log probability with respect to the simple distribution, which hopefully is relatively simple to write out, together with then the log of the absolute value of the determinant of the Jacobian here. So if you can do that and learn such this mapping via some parameters theta, then sampling also is very simple. You just sample from your simple distribution, and then to get a sample from your complicated distribution, you just calculate the inverse. And because remember F was differentiable and invertible, this also works out. And so the two axioms of normalizing flow are the fact that this is very simple to compute, and somehow calculating the determinant of the Jacobian is tractable. And so a lot of work in normalizing flow research is going into figuring out how to create neural networks such that these two properties hold. What I wanted to say in this picture is this idea that transforming a complex distribution to a simple one, and then sampling by going backwards. So sampling from a simple one to the complex one can be achieved through a composition of these bijections, right? So remember, if we have if all these bijections are invertible and differentiable, then their composition are also a function which is invertible and differentiable. So we start off with some complicated distribution on the right here, and then we have a very simple invertible transformation, say f capital K, some bijection that makes this complicated distribution just a little bit less complicated. And then the next bijection makes that distribution and even a little bit more, simpler, and so forth, till at the end you end up with a function that takes a very simple distribution here and makes it into a Gaussian, right? So since the composition of these invertible and differentiable function is also invertible and differentiable, we can put these we can kind of add these compositions like layers in a neural network to obtain bijections that are very, very complex. So they allow you to then map very high dimensional and complicated distributions into something very similar quite easily. So this takes care of the issue of this idea of composition takes care of the issue of having networks with enough capacity to kind of learn complex distribution, but we still have the issue of the determinant. The issue of the determinant is can be highlighted if you look at, for example, a linear flow, right? So a linear flow is nothing more than taking your data and multiplying it by some matrix A plus some bias B, right? So this, as long as A is invertible, this is inverse. This function has an inverse, so it's invertible, right? And its determinant of the Jacobian is just a determinant of A here. And so we have two issues here, that the determinant, and if we don't assume any structure on this A, then the determinant and the inverse are order D cube operations. So that doesn't work. But more importantly, the other issue with this data is that the composition of linear maps is also linear. So this doesn't have enough capacity in some sense to learn complicated distribution. So the bijection that I want to talk about, let me just turn on the light so that, hold on, so you can see me better. It's getting dark. All right. So the bijection I want to talk about is called real NVP. And it consists of what's called coupling layers, as shown in the diagram here, right? So it's initially it's a kind of daunting when you first see it, but it's relatively simple. You take your data set, which at this point is a vector of size capital D, and you split it into two pieces, a piece of size little d, and the other piece of size from D+1 to capital D. So what you do is the first piece gets mapped to the output via identity operation. So you just copy the X1 and Y1 are essentially the same thing. So that's the identity. The second piece here is now a function of only the first. The second piece here transforms this piece only via functions of the first piece. And so the first piece goes through a complicated neural network, S theta, as well as, so this is the scaling, what we call the scaling neural network, and then exponential function, and you multiply, you have you multiply element-wise with the input, and then add element-wise with the output from the transformation neural network. And that's how you define this thing, right? And so what you do is then you have many such coupling layers where you mix up which piece. So then the coupling layer after that, for example, might keep this piece to be the identity and and do the transformation on the other piece and so forth. So you mix up, in some sense, with many of these coupling layers, which pieces of your input stays the same and which one doesn't. And because S and T are neural networks of your choosing, they can be made as complicated as you want without wrecking the two properties, as I said, of normalizing flows, which I will show you hold here in a second. Right. Another aspect here is that you can also now incorporate conditioning. So you can learn a conditional model of XT by just concatenating some conditioning vector to the neural networks S theta and T theta. And that also works as well. Any questions here? None. Okay. Hope that's clear. So given these this kind of complicated mapping, how does this kind of help us? Well, it helps us because when we realize that the Jacobian of this operation is block diagonal. So, for example, if we calculate the Jacobian, I'll go back and forth on the slides now. So if you calculate the Jacobian, you'll see that one piece here is just the identity. So this is the gradient why is this? Yeah, so it's the gradient of this with respect to that, right? It's just going to be the identity. This doesn't depend on that. So the gradient of this with respect to that is going to be a zero block here. This piece here depends. Sorry, this piece here, the gradient of this with respect to this piece is something very, very complicated because it depends on the very nonlinear neural network S and T here. So this is something super complex and complicated. And finally, the gradient of this with respect to that is just because of this exponential is just going to be a diagonal block with the exponential coming from here. So now the determinant of this, so that's the Jacobian, as I said, it's block diagonal. But the determinant of this Jacobian, because of the fact that here we have a block of 0, that gets multiplied by this block. And so no matter how complex the two neural networks are, it doesn't matter. The determinant ends up just being the diagonal entries summed up like this. And because remember, we want to calculate the log determinant in our maximum likelihood estimate, then this exponential will also go away. So essentially calculating the determinant becomes very, very simple. And it's only a sum over the outputs from the S network. Calculating the inverse is also super simple because remember, if I go back, the Y1 is essentially gets copied here. And so it's you can use these Y's to then go through the T to then calculate what the XT will be as well. So calculating the inverse is a very simple operation as well. Meaning we can evaluate the log probability of our complex distribution tractably because the determinant is relatively simple to do, and we can add expressibility in this model by stacking many of these coupling layers, just like many layers of some other neural net, just like stacking other neural network layers. So the paper essentially uses these conditioning coupling layers to learn, in some sense, the distribution, the complicated multivariate distribution of the next time point by maximizing the log probability with respect to the very simple, the conditional log probability, where the conditioning is now on the past this way. Then you maximize the log probability with respect to the simple log probability of this next multivariate vector with respect to the simple distribution together with the determinant of the Jacobian, which is relatively, computationally tractable. In this way, you can learn the distribution of very high dimensional data, very high dimensional multivariate data this way, just like in DeepAR. And just like in DeepAR, we can also sample into the future by suppose we are over here, we then sample from our very simple distribution and then conditioned on the past, generate a sample of the very high dimensional distribution, which we can then pass back into the RNN and so forth to go into the future. And we can also replace the RNN by attention block as well, and that also kind of and that also works. And you can see that in the paper. In terms of results, then we obtain more or less state-of-the-art results on very high-dimensional multivariate problems with respect to very strong kind of baselines, as I said, that are using modern kind of statistical, very robust statistical kind of ways of modeling high-dimensional distribution, like copulas and so forth. But all is not rosy because so normalizing flows, as you saw, are bijections of invertible bijections, and so they impose a certain structure on the network. In some sense, the network has to be invertible. Also, normalizing flows, they assign infinite mass to discrete value data. So if your data, like the number of taxis or the number of page views is integer value, then it's also problematic as well. Also, recent works have shown that normalizing flows tend to assign high log probability to out of distribution samples as well. And so to use these methods for, say, anomaly detection task is also problematic. So that kind of led me to kind of explore the use of diffusion-based models, which is another class of likelihood-based models, which have recently shown to also generate high-quality samples from high-dimensional data, like images or audio waveforms. And it has a lot of desirable properties like distributional coverage, and the training objective is relatively straightforward, unlike in GANs. And so it's another great kind of class of models. And in fact, next week's talk at this seminar is going to be from someone I hope who will talk about, who's an expert in this area. So be sure to tune into that as well. All right, so as I said, on a high level, so I don't want to go into detail because I don't want to steal his thunder, but at a very high level, these diffusion models sample from a distribution by reversing a gradual noising process. In particular, sampling starts with some completely white noise signal X capital N, and you produce a slightly less noisy sample xn-1 and so forth, and you kind of denoise it until you end up with your final sample x0. So and as you sample, you can imagine this very noisy sample is some sample from some, say, Gaussian, and so as you take more and more samples here, you get more and more more samples from your data distributions as it's after training. And you parameterize this model via a neural network, and this neural network can be more or less anything, can be as complicated as you want, and there's no restriction on its structure. And this neural network takes some arbitrary noised ground truth data. So you have your data, you add noise to it, as well as conditioned on the level of noise, and it tries to predict the noise level. And if you can predict the noise level for each level, then you can imagine at this level, if I predict the noise, I subtract out the noise, and then go and put this back into the network to predict the noise, and then subtract out the noise and so forth, I can end up with my final sample that way. So in this way, these models can learn, because these neural networks can be arbitrarily complex, can learn very high, can learn these complicated distributions and give very high quality results that way. And then training is also relatively simple. You have your ground truth data, which is has no noise in it. You artificially, because you know the noising schedule, as I said, it's fixed. You artificially add noise to it for different levels, and then you learn then your objective from your neural network is the level of noise that you added for that particular noise level. And this way, you can train your models this way with a very simple mean squared error loss. Here's an example of how it looks like in the image setting. Right, in the image setting, you started out with noise and then slowly denoise it, and depending on the different noise kind of images, you end up with you sample different places in your data distribution that way, in a smooth way as well. All right, so the paper, the second paper, essentially tried to learn a diffusion model of the next time step based on the history. Essentially, what that meant is that now the neural network, apart from the noise level of your data for each time point, also gets the history coming in from an RNN, and then tries to then learn the distribution that way. And as I said, it's very much related to what the next week's talk and score matching, which is essentially a way of giving high probability score to where the data distribution is, and very little score to where the data distribution is not. And so it's also, these methods are very well suited for anomaly detection tasks. So as a picture, as a schematic of the model is essentially just doing that. At inference time, as I said, you're learning the noise that you add for each time point, depending on which data point is generated. And at inference time, you sample from the most noisy data, and then reverse this via this p theta network, and go back to a sample of your next time point. And then again, you can put this next time point back into the RNN to get the sample of, and then and go backwards to get a sample of your t+1 time step and so forth. And this gives again state-of-the-art results on probabilistic time series forecasting for very high resolution, for very high dimensional problems. So I'm going to finish by just saying that with these methods, one is able to utilize modern methods of learning high dimensional distribution in the time series context. Unlike GANs, with these methods, we have a concept of log likelihood, a kind of this likelihood score, which we can use for comparing and measuring performance, which is nice. And more importantly, these modern energy-based or denoising methods allow for more expressive network, allow us to incorporate more expressive networks, neural networks, rather than normalizing flows. And so a lot of domain knowledge or inductive biases of your problems can be added to your network. And you can also use it for the anomaly detection task, because essentially these energy-based models are kind of minimizing exactly that loss. All right, so I think I'll end here and be happy to answer any questions. So,
great, thanks, Kashif.
No worries.
Yeah, so is there any questions, comments, feedbacks for Kashif from the audience? Yeah, so there's a question from the chat, which is kind of long, I think, from Andre. The question
In some
is,
sense, there's a
the question is there a
bias.
sense of what kind of inductive bias you want in your architecture to have for the data domains you're
Right.
exploring? In some sense, there's a plethora of other invertible models to choose from. I think FFJord, which is like the continuous normalizing flow thing, I believe, Gaussianization flows, etc. Since there are a lot of these models have been used for images, do you have a sense of how to adapt the architectures for domains of interest?
Right. Yeah, so the two main things, at least in the time series setting, was the fact that you have data sets which are discrete valued, and you have data sets which are continuous, like floating point things as well. And so there you want to have some way of some inductive bias built in on the distribution modeling part, especially when it comes to normalizing flows, right? But unlike images, in my experience, time series data is typically not as complex as image data. And so in some sense, many of these other normalizing flow models would work equally well, if not better than real NVP, which is what I used as my baseline.
Cool.
Welcome.
Any other
on the
questions?
other hand,
Yes,
what's problematic is, on the other hand, what's problematic now is that I'm able to model very high dimensional data, the distribution at each time point. Now the problem shifts to how do I model its temporal dynamics, right? I cannot shove like a 1,000,000 dimensional vector into an RNN to model to get the hidden state. Whereas in some sense, I can model a 1,000,000 dimensional kind of image, which is, if you think about the number of pixels, I can model that easily with these normalizing flows. But how do I model its temporal dynamics is where now kind of the pendulum has shifted that way.
Any other questions? So Kashif, actually, I have a question for like, for instance, for EBMs, and especially like something like, I don't know, a score-based method, as you mentioned.
Right.
One thing that I think is a drawback to these methods is that because they rely on the gradient, like the gradient of the gradient information, right? Which means like for discrete data, they don't quite work. So basically, your method may work on time series, like financial time series or continuous modeling, but if we're applied today to discrete text or text embeddings, these kind of recurrent networks will not work. Do you have any good idea on how to improve over this?
No, but I saw a lot of work, I think at last year's iClear as well, on these methods for at least the text generation problem as well. And I think it's non-trivial, you're right, to get it working for these models, but I didn't go through those methods yet.
Okay.
I can send you the link. I have one in mind from Neighbor Labs that did that, I think.
No, I've also, I think, read a few of these papers, I think by, for instance, Will Grathwohl from Toronto and the Stanford people. But yeah, I just wonder, like, more generally, what do people think in terms of this, like, problem?
It would be good to ask Stefano next week. I think he's one of my academic heroes, as you can imagine. Not only his work here, but he's done a lot of work on humanitarian poverty mapping and also time series forecasting, which is kind of really awesome. So it would be something to ask him as well what his thoughts are. He would most probably know as well.
Got it. Yep.
Looking forward to next week.
Yep. And the other question I had is, like, basically in the first part of your talk, when you predicted this mu and sigma, right? Are you only like basically like constraining these first two moments of the distribution, like basically, so I let me see what I wanted to ask is basically how do you constrain that, for instance, how do you regularize this mu and sigma, right? Like, do you want, so typically, for instance, people use some KL divergence like in VAE. But in this case, I think you mentioned like you know its shape is like a negative binomial. But in this case, like how do you constrain this range of mu and sigma?
So I let the log probability do its thing, so I can backpropagate.
So you don't really constrain it, but just have it learn by itself. Okay.
Right. And the only thing I need to make sure is that, for example, the sigma parameter needs to be positive. So this thing goes through a soft plus and so forth. And so this part is just a linear layer that outputs two numbers in the end, given a vector. And then this second number just goes through a soft plus. With the negative binomial, for example, for count data, then both these need to be positive in some sense. And so both these go through a soft plus. And again, you can maximize the log probability of this distribution class with respect to some data and backpropagate through, so that a network will start to output sane values for the future, as long as the distribution there's no distribution shift. You will be fine. But apart from that, there's no constraint here. So I'm just essentially learning the data distribution that way. There's other aspects of learning the distribution, which is, Bayesian neural networks, which learn not the data distribution, but I guess the uncertainty that the model has and so forth, which is kind of orthogonal.
Right. Yeah.
To this.
Got it. Yeah, thanks. Is there any other questions, comments?
Hey, Kashif, I have a question.
Yes, of course.
In the second part of your talk, you mentioned that there was this convenient like block diagonal structure to the Jacobian. What is imparting that?
The fact that
it's the coupling?
This thing, exactly, the fact that this bit here is identity. So the gradient of this bit with the gradient of this with respect to this part is going to be 0, because it's just doesn't depend on this part. So meaning in the Jacobian, this piece of the big matrix is going to be all zeros. And so when you calculate the determinant, this 0 is going to get multiplied by this part and cancel out. And so you'll only end up with this diagonal bit where this is, and then you have to multiply all the elements. And this is because of the fact that this is kind of a linear function, right? So this bit is just a linear function. So the gradient of this with respect to that is just this thing, right? So you'll end up with just this thing coming out here. So the way, the smart way of kind of splitting this input into this output structure gives this this property, which is smart.
I see that now. I have another question. I guess kind of maybe related to the one that's in the chat. So other than the computational complexity, is the invertibility or local invertibility of this somewhat useful?
It has to be invertible because in the end, I need to go from very simple distribution all the way to my complex one, right?
Yeah, I just mean like, because it has this structure, you have this determinant, it's the sum over diagonals, and those are non-zero. And so you'd be able to, like the diagonal of this Jacobian, you would be able to show some invertibility, and it might be useful.
Right. Yeah, potentially. I didn't think about that. And then of course you need to mix it up, right? You need for the next one maybe, so you can also do it odd even odd. You can do this mixing of with respect to some odd even mass. You can do it with the splitting like this and so forth. So the more you then mix it up, the better the more expressibility or the better it has better chance it has in some sense to learn the dependence of these with respect to these and so forth in these layers. Is there a physical interpretation? Yeah, I wouldn't know of a physical interpretation.
Yes, I think there's a question in the chat. If you're responding.
Other than being, I think, was that you, Eric, who asked that and wrote it, or then being
I think it's Eric. Yeah.
Oh, okay. Ah, yeah. So awesome. All right.
Oh wait, sorry. So did you just say like there's no immediate physical interpretation that you're aware of?
Okay. Not that I'm aware of.
I see. Okay. Yeah. Is there any other questions or feedbacks for Kashif?
Yeah. So a lot of research in normalizing flows, at least, has to do with kind of learning these mappings so that those two properties hold. The fact that the inverse is easy to calculate and the determinant of the Jacobian somehow is simplified.
I always have this impression that the affine coupling layer that they first proposed like is a huge factor limiting this architecture, but I think it's since got improved a lot.
Yes, indeed.
So there's a new question. Do you think these methods can be extended to forecast spatial temporal data sets?
Right, I think so. I think so, yeah. So that's not my area of speciality in some sense, but I think it could be possible. One aspect I was thinking of was to learn, in some sense, the spatial kind of dependencies of these entities somehow by learning somehow the graph, some kind of interpretable graph, and then use that graph to do the prediction. So just ignore the coupling there. I'm just talking about these entities at each time point, and whether that would be possible to also have an interpretable kind of graph of the relationships between these entities as you predict and so forth. But a lot of the data sets I've been working with, there is no explicit graph there, and of relationships. So I have very limited experience in that field, unfortunately.
Cool. Well, if assuming there's no other questions or comments or feedbacks, yeah, so please join me in a virtual round of applause, maybe, for Kashif. Yeah.
No.